Section: Introduction. In this section, we delve into the realm of deep learning models and their reliance on large neural networks that require substantial amounts of data for training. The increasing complexity and cost of training these models have led to a rise in reusing pre-trained models for various tasks. However, the challenge lies in the fact that once trained, it is hard to remove specific data from these models, raising concerns about preserving outdated or harmful information and violating user privacy. Building efficient machine learning pipelines that can support data deletion requests poses technical challenges. The emerging field of machine unlearning aims to tackle this issue, but it is still in its early stages, and the factors influencing the success of different unlearning approaches are not well understood. Understanding what makes unlearning easy or difficult is crucial for selecting the right method for a given request. Sometimes, existing methods may not suffice, leading to the need for retraining from scratch instead of opting for imperfect data removal. By investigating the factors that determine the difficulty of unlearning, we discovered that the problem becomes more challenging when the retained and forgotten data are closely intertwined, and when the forgotten data is strongly memorized by the model. Different unlearning algorithms exhibit varying levels of struggle as the difficulty increases, revealing new insights and shortcomings of current state-of-the-art methods. Inspired by our findings, we introduced the Refined-Unlearning Meta-algorithm, RUM, to enhance unlearning pipelines. RUM involves a refinement step that categorizes the forget set into homogeneous subsets based on relevant factors influencing algorithm performance, followed by a meta-algorithm that guides the unlearning process for each subset to create a model that has successfully unlearned the forget set. Our thorough investigation demonstrates that RUM enhances the performance of existing algorithms and addresses the challenges identified in unlearning difficulty analysis. Section Summary. In this section, we delve into the challenges posed by deep learning models' heavy reliance on training data and the difficulty of removing data from trained models, leading to concerns about perpetuating harmful or outdated information and violating user privacy. We introduce the emerging field of machine unlearning, which aims to address these issues by investigating factors that affect the difficulty of unlearning problems. Our findings highlight that unlearning becomes more challenging when the retain and forget sets are entangled, and when the forget set examples are heavily memorized, leading us to propose a Refined-Unlearning Meta-algorithm, RUM, to enhance unlearning pipelines by improving performance and addressing identified issues. Section: Evaluating Approximate Unlearning. In this section, we will evaluate approximate unlearning. The success of most approximate unlearning algorithms cannot be proven within tight bounds. Therefore, the community has focused on empirical measurements of success based on three main criteria: good forgetting quality, high utility, and efficiency. Balancing these factors is crucial as there are trade-offs between forgetting quality and utility, as well as between forgetting quality and efficiency. A good metric for unlearning should consider these trade-offs. Measuring utility and efficiency is relatively straightforward and can be done by looking at accuracy on the retain and test sets, as well as the time taken, respectively. However, measuring forgetting quality is more complex. One simple way is to check the accuracy on the forget set and aim to match the accuracy that would be achieved by retraining from scratch. Another approach involves using membership inference attacks, MEAs, to assess forgetting quality. MEAs try to determine if a data point was part of the training data and then unlearned or if it was never seen during training. To comprehensively evaluate an unlearning algorithm, we need a single metric that considers both forgetting quality and utility. We will introduce a tug-of-war metric inspired by memorization. Deep neural networks tend to memorize some of their training data, which is essential for achieving optimal generalization error, especially with long-tailed data distributions. The memorization score for an example is based on how including or excluding it from training affects the model's predictions. Various approximate unlearning algorithms have been proposed to clean up data post-training. Fine-tune relies on catastrophic forgetting to reduce the model's confidence on certain data. Neg-grad maximizes the loss on specific data points, leading to a drop in utility. Neg-Grad Plus combines fine-tuning and gradient ascent to address this issue. Scrub extends this approach by framing it as a student-teacher problem. L1 Sparse introduces weight sparsity using an L1 penalty during fine-tuning. Influence-Unlearning estimates the impact of removing a data point on the model's weights. Relabeling-based methods trick the model into learning new labels for certain data. Saliency-Unlearning focuses on optimizing only the salient parameters of the model. Section Summary. In this section, we evaluate approximate unlearning algorithms based on three key criteria: forgetting quality, utility, and efficiency. Forgetting quality is measured by accuracy on the forget set or through membership inference attacks, MEAs, to determine if unlearned examples can be distinguished from never-seen examples. We introduce a tug-of-war metric to holistically assess unlearning algorithms, inspired by the concept of memorization in deep neural networks where certain examples are more highly memorized due to noisy or incorrect labels. Various unlearning methods like fine-tune, Neg-Grad, Neg-Grad Plus, Scrub, L1 Sparse, and influence-unlearning are discussed, each employing different strategies such as catastrophic forgetting, loss maximization, and relabeling-based approaches to improve the unlearning process. Section: Difficulty of Unlearning. In this section, we explore the challenges of unlearning. We look at previous research that studied adversarial unlearning cases, focusing on constructing difficult forget sets through interpretable factors like the entanglement between the retain and forget sets and memorization. While some studies aim to create more pessimistic evaluation benchmarks, our goal is to enhance our understanding of unlearning issues and how advanced algorithms behave when dealing with forget sets of different characteristics, ultimately improving unlearning processes. We also investigate catastrophic forgetting during training and its relation to privacy concerns. Previous studies have shown that models trained on large datasets may have better privacy protection for examples seen early in training compared to recent ones. Additionally, we examine forgetting events, where examples that were correctly predicted before become incorrectly predicted later, especially for examples with noisy labels. Models trained with differential privacy, DP, struggle to predict atypical examples accurately. Building on this, we focus on the difficulty of unlearning after training, rather than forgetting during training, and connect this to memorization and atypicality in the data distribution. We identify two factors affecting the difficulty of unlearning and introduce a metric called the tug-of-war, TOW, to measure this difficulty. TOW evaluates how well a model can forget certain information while retaining performance on specific sets. The entanglement between the forget and retain sets plays a crucial role in the complexity of unlearning. We propose an entanglement score, S, to measure this entanglement in the embedding space of the original model. Higher S values indicate more entanglement, making unlearning harder. To create forget-retain partitions with different levels of entanglement, we use a distance-based approach in the embedding space. By sorting examples based on their distances to centroids, we construct partitions with varying S values. Our experiments on CIFAR10 and CIFAR100 datasets with different architectures show that unlearning is more challenging when the retain and forget sets are highly entangled. Methods relying on relabeling perform poorly in highly entangled settings, as close examples in the embedding space can lead to incorrect predictions affecting both sets. Section Summary. In this section, we identify two key factors affecting the difficulty of unlearning. We introduce a metric called the tug-of-war, TOW, to measure the challenge of forgetting while retaining performance on specific sets. Our study focuses on the entanglement between the retain and forget sets in the embedding space, showing that higher entanglement leads to more challenging unlearning tasks. Section. The more memorized the forget examples are, the harder unlearning becomes. In this section, we delve into the connection between the level of memorization of examples that are forgotten and the difficulty of unlearning. We start by defining that if an example is not well memorized, the model's predictions on that example remain stable whether or not the example was part of the training data. This implies that unlearning is not necessary for such examples since the original model's predictions are similar to those of a model trained from scratch. On the contrary, for highly memorized examples, the predictions between the original model and a retrained model differ significantly, indicating that unlearning is more challenging for these cases. We explore how the memorization level of the forget set impacts the performance of state-of-the-art unlearning algorithms. We hypothesize that unlearning is easier when the forget set contains less memorized examples. To test this, we calculate the memorization score of each example in the training data and sort them based on these scores. We then create 3 forget sets: low mem, lowest scores; high mem, highest scores; and medium mem, scores closest to 0.5. We apply various unlearning algorithms to each forget set and measure the time of work, TO, required. We conduct experiments on CIFAR10 using RESNET18 and CIFAR100 using RESNET50. Our analysis reveals that for most algorithms, unlearning is easier for forget sets with lower memorization levels. Interestingly, relabeling-based algorithms show a different trend, performing better for highly memorized forget sets. When examining forget set accuracy, we observe that for low mem sets, the model can still predict the correct labels even after unlearning, while for high mem sets, the accuracy drops significantly post-unlearning. Our study highlights that different unlearning algorithms excel for different forget sets. Relabeling-based algorithms struggle with low mem sets, while other algorithms handle them well. We suggest that using different algorithms for different forget sets could enhance unlearning performance. This research provides valuable insights for improving unlearning algorithms based on the memorization levels of forget sets. Section Summary. In this section, we investigate the relationship between the level of memorization of forget sets and the difficulty of unlearning. We find that unlearning is easier when the forget set contains less memorized examples, as shown by our experiments on CIFAR10 and CIFAR100 datasets using different unlearning algorithms. Notably, we observe that different algorithms excel for different forget sets, with relabeling-based algorithms struggling on low mem sets but performing well on high mem sets, suggesting potential improvements in unlearning by tailoring algorithms to different memorization levels. Section: Refined-Unlearning Meta-algorithm, RUM, for improved unlearning. In this section, we introduce the Refined-Unlearning Meta-algorithm, RUM, for enhanced unlearning. We have noticed that different unlearning algorithms behave differently when dealing with forget sets that have varying characteristics. For instance, some algorithms struggle with low mem forget sets, while others excel with high mem forget sets. This indicates that the choice of the best unlearning algorithm depends on the properties of the forget set. In real-world scenarios, forget sets are likely to be more diverse, containing a mix of examples from various data distribution modes. To tackle this challenge, we propose a 2-step approach with RUM. Step 1. Refinement. We use a function to divide the forget set into homogeneous subsets based on factors that influence unlearning difficulty and algorithm behaviors. Step 2. Meta-unlearning. After obtaining the subsets, we need a meta-algorithm to guide how to unlearn each subset and combine the results to achieve complete unlearning. We focus on sequentially unlearning subsets in this work, leaving other approaches for future exploration. Our RUM framework involves selecting the best unlearning algorithm for each subset and determining the order of unlearning requests. By executing unlearning requests in a sequence, we aim to unlearn the entire forget set effectively. We present specific RUM implementations that leverage memorization scores and experimental evaluations to address key questions about the effectiveness of refinement, the impact of selecting the best performing algorithm for each subset, and the reasons behind the performance improvements observed with sequential unlearning of homogeneous subsets. Section Summary. In this section, we introduce the Refined-Unlearning Meta-algorithm, RUM, to address the challenge of unlearning heterogeneous forget sets. RUM consists of 2 steps: refinement, where forget sets are divided into homogeneous subsets based on factors affecting unlearning difficulty, and meta-unlearning, where a meta-algorithm dictates the unlearning process for each subset. By sequentially unlearning subsets using a pool of algorithms, RUM aims to improve unlearning performance by adapting to the properties of the forget set. Section: Experimental Setup. In this section, we experimented with a refinement strategy based on memorization scores where we set K to 3. Specifically, we focused on unlearning a forget set S that includes the n lowest, the n closest to 0.5, and the n highest memorized examples in the dataset, where n is 1000, making the total size of the forget set 3000. We conducted experiments on two datasets, CIFAR10 and CIFAR100, using RESNET18 and RESNET50, respectively. We evaluated unlearning algorithms based on TOE and a commonly used MIA metric. The MIA metric measures how well a binary classifier can distinguish between examples in the forget set S and the test set D_test. Our goal was to match the MIA score of unlearning with the MIA score of retraining from scratch. We also analyzed the impact of different orderings, low to medium to high and high to medium to low. To explore the effectiveness of refinement alone, we selected the best performing algorithms and applied each algorithm in 3 ways: standard application, sequential application on randomly determined subsets of S, and sequential application on subsets obtained through a specific method. We observed that for various unlearning algorithms and datasets, the sequential application on homogenized subsets according to memorization scores significantly outperformed standard and randomly sequential applications. This suggests that operating sequentially on homogenized subsets can enhance the performance of unlearning algorithms. To further improve performance, we identified the best unlearning algorithm for subsets of low, medium, and high memorization scenarios. By incorporating these insights into the unlearning process, we achieved the best results by applying a specific sequence of algorithms. We also observed that the performance can be enhanced by selecting different algorithms for each subset based on their memorization levels. We analyzed the dynamics of different orderings in terms of TOE and MIA. While TOE remained similar for different orderings, MIA showed variations. By examining the accuracies on the forget set and its subsets after each step, we gained insights into why certain sequences of algorithms outperformed others. We found that the sequence dynamics play a crucial role in the performance of unlearning algorithms and may have helpful or harmful effects on TOE and MIA. Further research is needed to delve deeper into these sequential dynamics and their impact on the overall performance.